Hello everyone, and welcome to the ninth tutorial of the Functional Data Structures course. Today we have two exercises, one about red-black trees and the other one is about 2-3 trees. So I will just start now. So recall the insert function of the red-black trees. We want to change it into a function that, so this is the original insert function. We want to change it such that if the member that we're inserting is in a tree, the function returns none, otherwise the function returns a new tree with the extra element inserted. So let's do that. So the first case is when when the element is less than. Okay, so and then this is when it's greater than. So the first easy cases. Okay, so there should be none if what you're inserting is an element that already exists. And here also is the same. And then here it should be split. So it depends on what the insertion is. If it is none, then we return none. Okay, so you insert it in the left, and then you see if it is none, then you return none. Otherwise, you return the result of the rebalancing. So let's just copy that and then see. Let me just make sure that this case doesn't have arrows. Yeah. Of course, this should be some t. Should be some other key. So, and then I'm just looking into what's wrong there. Yeah, because I forgot to actually get that to be an option. So it should return an option type, yeah, so now it works. And now let's change the other case, which is this one in the original insert function. So here we have that. So this is an insertion into a red node, so the same should happen. So it's equal, we should return none. Otherwise, we should do as we did here. Same there. Okay, so that's the definition. And now we need to prove that if the given tree is an actual red-like tree, say if it has a variant of colors, then basically we want to show that if it returns none, then the tree had the element. If it doesn't return none, then yeah, we should also call this insert prime, by the way. So just insert prime. Okay, and then we need to show that insert prime basically operates correctly. Okay, so let us try and do this proof by induction. So I will just try and do it by induction on the tree. On the given tree. See what happens. Let's write O2. Okay, so we need to split an option using option splits. Okay. So now the subgoal. If the insertion of some x in okay. So here we need to, my guess is, we also need to do some, like we need the different cases of x compared to a, maybe. So in order for us to get those different cases, instead of doing everything over the cases manually, we can just do the induction using the schema that is generated by the function. So this will hopefully give us clearer cases. Yeah, so now we have the comparison results. So I'll just hammer down and see if it can be proven. If we have a problem. Okay, so sledgehammer found something. So if sledgehammer found something, we better find something better. So this balancing function we need, in order for it to work, we need to split the case, consider different cases of T2. So in order for us to consider the different cases for T2, I'll just do this for testing the proof, but then we need to clean it up. Okay, so I'll just say subgoal X LA R. Okay, and that's just to make sure that we can take the cases on this R. Apply cases on R. And then what is going on now? And then here we probably need the cases on the color as well. The color B. Let's just go back earlier. We also need to split cases in L. Okay, so now we have something closer to the definition of balance I R. Let's take hammer now. So color exhaust means that we need to split cases on the color as well. So what is the name of the color here? Those two colors. So maybe we can just do a like a lemma before we start that proof, and that lemma should just talk to us about the like the value of B, that value there. So let's now try and figure out what that lemma should look like. So, so when is this balancing equal to blue, equal to black? So it should just be when the left and the right both conform to the invariant of the color. I think that should be it. Now we can. Yeah, we need to. Cases on the R, I think. Yeah, in order for us, let us just do it by induction. So we need now to just do consider all the cases that come from this balancing function. So we can do it by induction on those. cases with the rule. So how does it look like? Yeah, it does it. So all that I was doing here is just because, as you have seen in the original proof, I was trying to get this definition to be expanded, but there's no way for you to do that without having those trees, like those trees written in like the case. Like there's no way for us to have done that without splitting all the cases on the right tree. And the easiest way is to just use the induction principle that comes out of the balancing function. And the same. So let's just use that lemma. So here we have that, and then I'll just edit this simplification. Yeah, we need the same one for L as well. Symmetric one. Yeah, and then here I should just add this as an L. Yeah, that does it, and that finishes that exercise. Okay, so now I'll go to the next exercise. Now let me start with the second exercise. So in this case, so here we want to do a function that joins two 3 trees. So remember from our last exercise we did that, but in this case we want the 2, 3 trees to be over all arbitrary heights. As in last time we assumed that both trees are of equal heights. This time we assume that they are of potentially different heights, and we also are given a root node where we are supposed to join the trees. So in particular, so let me just try with drawing. I'll assume that you somewhat remember our last tutorial, otherwise you can just go to the video and recheck it. So here we have here we would have a node and the left tree and and the right tree. Okay, and then in the first case I'll assume that that the height of this one is bigger. Okay, and so if the height of this one is bigger, then you will be starting here and there and there, and then you should be descending that left spine until you reach a point in the left spine where the rest of the tree, starting from that spine, so basically this, has the same height as that height, okay, as the height of the left, so, of the given left tree. And then once you reach that stage, you need to connect this subtree with that, with this as a root. And the way you do that, if you remember, we create an overflow. Okay, that's with that root in the middle, and then this one is the left, and that one is this one there, and then that one there, and then you go up. And if for example the parent of that node here where you stopped is a 2 node, then you just simply insert, you turn it into a 3 node, and then insert those subtrees. Otherwise you keep passing the overflow until the top level, and then you create a new node. Okay, so let me quickly do that. So you have join, I'll just call this as we have in the sheet there. So here I will just call this function as we had in the sheet. So join L, okay, this is the function, and then you have it takes a left and then X and then R, and then if the height of the left equals that on the right, then we do as I said here, we return overflow, okay? And then now if the height is not the same, what you will do is that you will recursively that you will descend on the spine as I said here, and the way you do that here is that we could do like a case matching. So for example, you can say if cases that the right tree is a node 2 of let me just call it T1 and V and T2. If it is like that, then you will just call the function join L on T1 and L, so what you do, so else case is L R of this, and then you would again call the function join L on L and X and T1. So here we're going like that, and then this is the same, and then you again will see what the result of this thing is. Okay, so it could be an overflow, and since or it could be an insertion. It could be a successful insertion without an overflow. So if it is not if it is a successful insertion, what we can do is we just join. Well, actually, let me just do this. So here we will check the two cases of join L. Okay, so if join L is a successful insertion, okay, so Ti of just a T, then what we should return is the same node, so if it is a T, so basically this thing became somewhere below us into a T, okay, somewhere down there. Then you just simply replace this left subtree with the T, okay, so you will have T, VT1, VT2, sorry, and if the result of this joining is an overflow, okay, then in this case, so an overflow with, what should I call it, like an L prime, an X prime, and an R prime, then in this case I will simply turn this node into a 3 node, so it would be node 3, and we would have L prime, and then X prime, and then T, and then R prime, and then V, and then T2. Okay, so let's just do that. So we have join L, so join L XR equals So if the heights are the same, we just return and overflow. So else we do a recursive call of join L. What we let me just try it to make sure that everything is processed. I don't think so either. Parentheses there. And I'll just okay, so here we just see what is the right tree is. So if the right tree is node 2, T1, V, T2 in this case. Join L. We call it an X and an X in T1. Okay, but we don't really do that. We see what returns from that call, and then so if what returns from here is just that successful insertion, then we return the same node, but with that replaced, with the subtree replaced with the successful insertion. So we have okay, let the types work. Otherwise, it is an overflow. We extend the node. And in the case, it's a 3 node. Okay, so now in the case, what comes out of this recursive call is a 3 node. We will do a very similar thing. Okay, so sorry, in the case of the right tree is a 3 node, we will do a similar thing in that we will do again the same recursive call where we're descending on the left spine there. But and if it returns a TI, we just replace the left subtree with whatever was returned. And here actually no. Okay, otherwise if it returns an overflow, then you will need to return still an overflow. Right. So that overflow should look like, it should be a node 2, basically like what we used to do in the other case, in the previous tutorial. So here it will just be an overflow and then v1, and the second node 2, t2, v2, t3. Okay, and that should be the function. Okay, so now we need to make sure that this joining function works. So we need to prove two lemmas that basically preserves balancedness, and it preserves the element and the ordering of the elements. Okay, so let us start with showing that it preserves balancedness, or as it's called for 2-3 trees, completeness. Okay, so here we can do this proof by induction on the right tree. So we need to do split cases on split. What is it again? Just make this a bit bigger. On that type. So what was it called? Applying splits. Let's see. Yeah, so it does that. And that's the first theorem. The second one is to make sure that we are preserving all the elements and their ordering as well. Okay, so we'll just do an introduction. Okay, so you can just try that. Yeah, does it? Okay, and then we need to do a similar function, but when the left tree is taller, so it'll just be the symmetric, everything will be symmetric there. So here we have, first let me just call this join R. And then here you will be splitting the cases on the left tree. If it is like that, then you will descend on T2 and R. And if what's returned to us is that Tutor R, we will just replace this. So this should be T1, V, and T. And the O3 case will be also the symmetric one, which is T1, V, L prime, X prime, R prime. Okay. And here again, we should be doing it on T3 and R, and again we just replace T3. It's an overflow. Then we just have T1, V1, T2. T1, V1, T2, and then V2, and then L prime, X prime, and then R prime. Okay, and then this should be also symmetric, and that, and that. Okay, it doesn't work, so we had a specific problem there, but probably not showing L, of course, because that is the function, but yeah, it works. Similarly here, we'll do the symmetric thing. Okay, so that does this. And now the remaining thing is to create a function that actually does join any two trees and an element which are of arbitrarily different heights. So that function should just basically it should just do case splitting. So join L, X, and R equals, and then it should be an if and else basically. So if height of L is smaller than or equal to height of R, then we call join L LXR else so we actually want to return that tree. So we'll just remember there's this function that given that type up I, there's a function that returns to you the tree given that. Let me just show you what function that is. So that function basically either creates a new tree if you have an overflow, or if you have a proper instruction then you can see the tree. So this is the tree that we're after. And now just that. Okay. So and now we need to prove that this function really preserves balancedness. So let me just do it. Here, what we want to do is to reuse those lemmas, this lemma and the other one, and that one, and so in order for us to reuse this, let's just try auto. Like, we don't want this explosion here, where basically I don't want the definitions of join R and join L to be expanded. So just do sim delete join, remove their definitions from the sim set. Okay, and now we have that. Okay, so actually there's an interesting thing that I forgot to talk about. We'll talk about it briefly. So here, look at this theorem statement there. Okay, so we wanted to only prove a completeness, but in order for us to prove completeness, we need this second assumption. Okay, look, the proof will fail. We basically are here. We are strengthening our induction hypothesis by adding an x, by basically strengthening the theorem statement that we want. So in order, we cannot prove this only this by induction. We have to prove this conjoined with that by induction, if that makes sense. But on the other hand, we want now to use this, only this conclusion of that theorem. So one way to do that, you can just do it. You can honestly, you can just let's just try this and the other one. So basically, you want those two theorems. I think you should be able to do it by glass or something like that. Let's see. Force. Okay. Yeah, force can just do it. So we now have the two theorems for the two different cases. This case is that, and that case is that. Okay, but in particular, we actually just want the first conjunct from that theorem. So one way to do that is by using this theorem, conjunct 1 of whatever, and that what that theorem does is it returns to you if you have a conjunction. So let me just show you quickly. So that theorem, conjunct 1, it says that if you have a conjunction, then the first conjunct is true, and then you can give it as an assumption a conjunction, and then it will just give you a theorem of the first conjunct only. So that's what we have there, the first only, and then we can do this also there. We'll just clarify things. So now we have that. And maybe you can just also do that. No, it doesn't. Also doesn't do it. Yeah, so we can just do it like that. Okay. And for the second theorem, we have a similar situation. So we have completeness of both things, and then we just want to show that the ordering is preserved. Okay. So here we need those lemmas instead. Yep. Okay, and that should be it for that exercise. So that's the final one. Yep, that's the final one. Yep, I hope you have enjoyed it, and if you have any questions, again, just ask them on the piazza or my email. Thank you very much, and talk to you next time.